The purpose of this lab was to observe the effects of gravitational force and drag force. I observed the motion of an object that was dropped from rest and fell somewhat slowly and straight down. The main result was that the computational model was a more accurate prediction of the actual motion of the objects when the force of drag was factored in, instead of only factoring in air resistance. Here, I videoed my friend dropping an Expo eraser. And we can track the motion using tracker. And the frame rate was 30 frames per second, and the time of last observation was 0.968 seconds. I oriented the axes so the object would be moving in the negative y direction, and I used the calibration stick, which is here, to make the motion of the eraser to scale, which was 0.1 meters wide. I constructed a computational model based on physics principles, namely Newton's second law, that includes only the effects of gravity. As you can see in the code, I specified the object's mass, the initial conditions for position here and velocity here, and I also specify constant g for the magnitude of the weight force. And in this model, we're assuming that the weight force is the only force that contributes to the net force. And if we run this model, we see that the curve shows that there is gravity in the negative y direction. For the computational model, I set b equal to 0.019, which is the constant of proportionality when I had drag force, and set b equals to 0 when I did not have a drag force. I predicted the drag force in this line, and then the net force. And then I used Newton's second law to predict the new velocity, which is this equation. And then lastly, I predicted the new position. And if we run this code, we see that the yellow arrow representing the weight force is in the negative y direction and not changing in direction and magnitude. The blue arrow, representing the drag force, is not visible, but then it appears in the positive y direction, and it gets longer as time progresses. As the object is up, the drag force becomes more significant. Here I plotted the falling eraser position versus time. The green dotted line is the observations, the blue line is the model with drag, and the red line is the model without drag. The computational model overpredicts the observations, and that it indicates that the object fell further than it actually did. As you can see, as time advances, the model's curve is stronger than the observation's curves. The model with drag does a better job of predicting the observations. It starts at the same position and ends at nearly the same position, right here. It also follows just about the same curve route. For the what does it mean question, I found that a terminal velocity exists when the model is calculated with the drag. With this model, the velocity becomes constant, and this is because as the object falls, eventually the drag force will equal the force of gravity. This will make F net equal 0, and the ball will fall with constant velocity after that time point. For the what if question, if the object was dropped with an initial velocity that was not 0, and in this case I chose -2 meters per second in the y direction, the same thing will happen. The object will reach a terminal velocity only when the drag force is accounted for. The object reaches a terminal velocity faster when given a velocity that is not 0. However, the actual terminal velocity is the same.